tremendous amount of experience testing steam traps, so we're really pleased to have Tristan take his time out of today, so thank you, Tristan. A little bit about UE Systems first. We were founded back in 1973. We've got 35 years of experience with ultrasound, one of the tools we're going to go through today in testing of steam traps. We've got a really large global footprint with 12 direct offices and about 200 independent distribution points around the world. So no matter where you're at, we can probably get out and help you with whatever it is you need. A little bit about Swagelok Energy Advisors. They do engineering services. They do steam system audits. They do some project management, and they also offer an entire host of training programs. What are we going to cover today? We're going to go through why steam, what are steam traps, what do they do, why do we even need to test them, and then how do we test them. There's the meat of it for today. If you have any questions while we're going on, you get a control panel over on the right. You can type in your questions, and we will try to get with you just as fast as we can. If we don't get to them during the webinar, we will actually be responding to them later as fast as we can, so be a little bit of patience if we don't get right to you right away. You can always actually contact Swagelok Energy Advisors after the webinar as well for any questions they might be able to assist you with. So enough of me. Let's welcome Tristan from Swagelok Energy Advisors, and we will actually begin. Tristan?
Okay, thanks again, everybody. My name is Tristan McCown with Swagelok Energy Advisors. I've been with Swagelok about 15 years now and working on the energy side of things for about the past 10 or so with Kelly Paffel and Swagelok Energy Group. Basically, as Gary mentioned, our main goal today is just kind of touch upon how steam traps work, a little bit why we're testing them, and oops, sorry about that. There we go. And touch upon why we're testing them, how to test them, some of the best test methods, and some of the different tools that we have available to us. So the first thing that we want to focus on is why are we using steam traps in the first place? Well, steam traps has three main functions. Primary function is remove condensate as quickly as it forms, and the second function, prevent live steam loss. Third function of a steam trap, and it's kind of a tertiary function, not the main function of the steam trap, but it has to be able to do this, is remove air from the system. We want to make sure we've got other devices in the system to get air out as quickly as it forms, but steam traps have to be able to do that as well. Okay. So when we're talking about the steam trap itself, the three basic functions I mentioned: vent gases or non-condensable. The non-condensable gas is air that occurs during shutdown of the system when the vacuum's pulled, or as the boiler makeup order discharges gases into the system. Have to do that in order to improve the efficiency of the system. Gases in the system other than steam are going to reduce pressure, and it's ultimately going to reduce temperature, so we don't have as an efficient system running. If we don't discharge condensate, we can back condensate up in the system. It's going to affect heat transfer equipment and may also result in water hammer. And then the last thing that we want steam traps to be able to do is trap steam. If we just have the line opener, that steam trap's blowing through, then the steam doesn't stay in contact with the heat transfer equipment long enough to give up its latent energy. And in a steam system, it's the latent energy that does all the work. That's basically the energy required for the liquid to change state from the liquid to the gas. And that's a large component of the energy in steam, and that's what makes it so efficient. So if we don't trap that steam and give it time to give up that latent energy, all we're basically getting out of the steam is the heat energy out of it. Okay. Why are we testing the steam traps on a regular basis? Well, we have to maximize the production rates and quality. In today's economic environment, if we are not running full out as best we can and as efficiently as possible, somebody else down the street is going to be doing that, and if they can do it more efficiently, then it's obviously bad news for our facilities. We have to maintain safety. I'm up here in the north part of the world, up in Canada, and we're sort of coming into our winter season here. If we get steam traps that are blowing through and dumping to the ground, anytime after mid-part of October, we start seeing a lot of the steam. As the steam comes out, it starts to create icing issues. It can also create fog clouds as we're coming through. And obviously, steam discharging in a facility is going to create problems. I don't know if anybody, it seems whenever I go out and do training courses, Die Hard seems to be on the hotel movies when I'm running through. And you think back to Die Hard, most of the scenes in the industrial facilities there, all you see is steam leaks coming out. That's kind of the standard view that most people have of steam systems, is leaks. And it's unfortunate and it's not safe. Obviously, walking through a cloud of steam can obviously be very, very dangerous. And then maximize energy efficiency. That's going to be a big one as well. If we are putting extra BTUs into that boiler to produce steam that's just warming up the ducts as they fly by, then again, we're obviously not being as efficient as we can possibly can be. We're wasting money and having issues there. 10 years ago, Fortune magazine came out, and this is 10 years ago when steam costs were very, very low. We're talking like $2 per 1,000 pounds. Nowadays, we're seeing prices typically in the $10 to $15 per 1,000 pounds for steel, or excuse me, for steam. Fortune magazine reported that a DuPont facility saved over $1 million a year just by testing and repairing defective steam traps. You know, we talk about the amount of steam that can come through one of these traps, and it's a huge, huge amount. And if the dollar figure doesn't kick something in, or you're saying, oh, well, we're just burning waste fuel or something along those lines, and the other side of it we have to think about these days is the emissions. There's huge, huge numbers of emissions that are coming through in the CO2 and the NOx side of things if we aren't checking these traps and making sure our steam system's running as efficiently as possible. Okay. So again, why implement a regular trap survey? Well, safety is going to be the primary driver. Improve the process efficiently by effectively removing the condensate. If we have a slow startup, or if we're allowing condensate to build up on our heat transfer equipment, we're not maximizing our production. We're slowing things down. We're making it tough to control the temperatures of the product that we're running through our exchangers. We want to maximize the cost and energy savings as well. Obviously, every dollar we can save coming in to the boiler that we're spending on fuel, $1 savings on fuel is the equivalent to $10 in sales. So it's a 10-to-1 ratio there. Obviously, everything we can save coming into the system is going to improve our bottom line on the outset. If we test on a regular basis, well, we're going to reduce trap failures. There's a number of traps that don't react well with back pressure. If we can come in and fix traps proactively, we can help prevent some of the false failures that we may see just caused by back pressure in the condensate return system. We can get control of maintenance costs. By being proactive on these systems, we can come in and obviously a predictive maintenance program is going to be less costly than a reactive maintenance program. We can control our costs. We can budget things a little bit better. We can work our way through the system. We're not worried about downtime and overtime and issues like that. We can also find sources of previously unrecognized problems. When we come in and look at steam traps, one of the things we really focus on is not just componentize the system. When you're doing your steam trap survey, you may find a trap that's failed. If you don't look at the system as a whole and you just replace that steam trap with the exact same one, chances are it's going to fail again in the same way. So when you're coming in doing a steam trap inspection survey, it gives you an opportunity to look at specific areas. So if there's a trap failing on a regular basis, and when we look at steam traps and any component in the steam system, we demand 6 years life expectancy out of it. If we're not getting that, then something's going on. We need to take a look at the system. So when you're doing the survey, if you're seeing a trap that's failing on a regular basis, then we're going to want to come in, take a look. Maybe there's something wrong with our piping. Maybe there's something wrong with the layout that we've got. Maybe there's another component in the system that's causing us grief. And by checking the traps on a regular basis and seeing where the problems are occurring, we can maybe get better efficiency out of our system as a whole. As I mentioned before, prevent unexpected downtime. Obviously, downtime is a huge, huge cost in the production world. So by being proactive and testing the traps on a regular basis, we may prevent a problem occurring down the line. Okay. One of the big questions that we get all the time is, what is the best way to test a steam trap? And ideally, we want to use 3 methods. We want to use visual, temperature measurement, and ultrasonic detection. If I only have one tool available to me, it's generally going to be ultrasonic detection, simply because I can clearly detect the sound of a passing steam trap in a piping system that's closed. I don't have to open valves. I don't have to break pipe. So if there's not a tool in place to see what's going on, then I'm going to use ultrasound. Temperature gives us some resources, but it doesn't give us a complete picture. When we come in and testing steam traps with ultrasound, what we're generally going to do is set our gun up initially at 20 to 25 kilohertz. That's typically a really solid starting point. Obviously, depending on your particular system and the background noise and the operating conditions, you may have to tune that in a little bit. But if you start at 20 to 25 kilohertz, you're going to be at a pretty good starting point. When you're looking at the sensitivity, generally with a lower pressure, our sensitivity is going to be higher. And with a higher pressure, we're going to go with a lower sensitivity. We'll talk a little bit about the testing methods coming up here in a few minutes. My preferred method is a comparative method. I find that seems to give us the clearest picture possible as we're running through. Okay. So as mentioned, the best way to test is to use all 3 technologies. Test valves are some visual indications, sight glasses in the system, temperature, which will tell us if we're getting live steam to the system, and then ultrasound to hear what's actually happening in that steam trap. If we're looking at temperature, there's a couple of different tools that we can use there. Infrared's one of them. What this will tell us is if live steam is coming to that steam trap. It won't tell us if that steam trap's passing through, or it's very, very difficult for infrared to tell us if that steam trap is passing through. Basically what it tells us is if we look at where that square number 1 is and related to the chart on the right-hand side, it shows we're running around 400, 416 degrees, which kind of off the top of my head here is about 140, 150 psi steam. There's a direct relationship between temperature and pressure. So if we know that steam system is running in that 400 degree mark, and that's roughly where our pressure is supposed to be in that 100, 150 degree range, then perfect, we got live steam coming to it. What will happen is if that steam trap has failed in the closed position or is being plugged up somewhere along the line, that trap is going to be considerably cooler than the steam pressure that we're dealing with or steam temperature that we're expecting to see. A 100 psi steam system is going to be 338 degrees Fahrenheit. If I come in with the infrared gun or temperature gun and it's telling me my steam temperature or my trap temperature is in the 150 degree range or ambient, then I've plugged the line up somewhere. So it tells me that trap has failed in the closed position. It won't tell me, though, if that trap has failed open. So if I come in, again in this situation, I'm at 400 degrees here. It's about where the steam pressure is supposed to be, say 150 psi. Looking at the outlet, it's obviously getting to be a little bit cooler, call it somewhere in that 300 degree range, so maybe 75 psi. All that's telling me is my condensate return system is running at a 75 psi pressure. As we come through the orifices of that steam trap, the steam gives up its, or the condensate will give up its energy almost instantly and drop its pressure down to whatever the lower pressure is. So it's very, very difficult to use infrared or temperature tell if that trap is blowing through. So we're only getting a partial picture by using infrared. It's a very important tool, and we have to use it to make sure we are getting live steam to the system and we haven't plugged that trap up. But after we've confirmed that we have live steam coming there, it doesn't tell us the complete picture if that trap has failed in the open position. So infrared's one tool. A little bit more of the more common tool is going to be the non-contact thermometer, similar to the one shown in the picture there. They're a little more cost-effective than the infrared. You obviously don't get as nice of a picture as you do with the other one, but for what we're doing with steam trap testing, it tends to be a little bit of an easier unit to work with. When you're looking at these units, just a couple things to watch for is make sure you have a good spot-to-distance ratio. Basically, that's the optics inside the gun. These guns will range in price anywhere from kind of the $30, $40, $50 ones you can pick up at the local hardware store, right up to $4,000, $5,000, $6,000 for the ultra quality and heavy duty industrial ones. So the basic difference in the price is the quality of the optics that you get into it. So by that all I mean is if you're 20, 30 feet away, if you have a 50-to-1 spot-to-distance ratio on one of these guns, for every 50 feet you move away from the object you're testing, you'll have a 1-foot diameter of temperature range that you're searching for. If you go to the lower optics guns, which may be down 2-to-1, 3-to-1, 4-to-1, for every 4 feet you move away, you have that 1 foot in diameter. So obviously for a smaller steam trap, the tighter that diameter is, the more accurate of an image you're going to get, or a more accurate picture you're going to get of the actual temperature of that device. One of the other things to watch for with these units is make sure if you are in a facility that requires an intrinsic safety, basically you're in an area that has potential for explosion because of the gases that are around or the environment, then you're going to look for an intrinsically safe device. And these ones are available with intrinsic safety. It's going to increase the price a little bit, but an extra couple $100 to make sure you're not blowing your plant up is probably money well spent. Okay. Second thing that we're going to do is, after we've confirmed that we do have the live steam coming to the steam trap, then we're actually going to listen to it. We can use a contact method. With these ultrasound units, as most people probably know, you've got the headset on, which is going to eliminate the background noise. Ultrasound units listen to the frequencies 20 to 100 kilohertz, which is above the normal human hearing range. So the headset eliminates the background noise, and then we just hear what's actually happening inside that piping. With the ultrasound gun as well, we're going to get 2 indications. We're actually going to hear what's coming through, and then we can also watch the meter. So depending if we have an analog unit, we can watch that needle moving back and forth. On the digital, we're going to have that bar graph that's going to show us what's going on, and we're also going to see where the decibel levels are at. So we can watch both of those to hear and see what's actually happening as that trap cycles through. Okay. When we get into testing, there's 2 main things that we're testing for ultrasonically with the steam traps. And there's 2 modes of operation. There's a number of different traps, but they all fall into one of these 2 modes of operation. There's either on-off, which means the trap's going to discharge, close for a time cycle, then discharge condensate again, close, discharge condensate, or a continuous flow when we're discharging condensate continuously. Most of the traps that we're looking at are going to be the on-off style. The only type of trap that we see with continuous discharge are the flow and thermostatic traps. Okay. There is a flow chart available. I believe this is on the UE website. I'll kind of run you through here quickly how it works and what we're doing when we're testing the traps, and then we'll get into the different types of traps, see how they work, and then we'll kind of run through a testing process for each one of the different types of traps. Okay. So we'll start off, and we'll want to make sure that the steam trap's operating. We'll do that by going back, checking the valves, make sure that they're all open. We'll then take the temperature. If the trap is cold or below operating steam temperature, then we know we're either plugged or partially plugged. Okay, so we can call that trap failed. We don't really need to listen to it at that point. If we're below, considerably below the operating temperature, the steam pressure, then we can call it failed in the closed position. If the trap is hot or close to the steam pressure, then we can move on to the ultrasonic testing. We're going to want to select the sensitivity for the steam pressure or use the comparative method, and we'll talk about selecting the sensitivity in just a minute here. And then we'll select the test procedure for the following. If it's an on-off trap, which is an inverted bucket, a thermodynamic, or a thermostatic trap, we'll listen for on-off operation. If it's the big flow and thermostatic trap, or even a smaller flow and thermostatic trap, we're going to look for more of a continuous flow coming through there. So we'll listen on the discharge orifice for either an on-off cycle or a continuous flow of the condensate coming through the trap, and we'll record the results. Okay. One of the big things to note is the closer we can get to that discharge orifice, the clearer the ultrasonic signature is going to be for that trap. So depending on the type of trap that you're working with, we've kind of got the pictures taken here, or some cross-sections taken here of the different traps. So that's roughly where the discharge orifices are going to be on the different styles of traps. If you have any questions about the type of trap that you're looking at, find the manufacturer's literature. There should be cutaways in there, and it will give you a pretty clear image of where that discharge orifice is on the type of traps that you have in your facility. But this is kind of a quick guide for a lot of the standard traps that are out there. Okay. As I mentioned, my preferred method of testing and setting the baseline is using the comparison method. As you get into the different steam systems and different steam pressures, the amount of noise in the lines and in the piping can be considerable. So what I like to do is I'll come in and I'll get my baseline reading. So I'll test over on the right-hand side where this arrow over here is. And what I'll do is I'll set my baseline reading at about 10 to 20% of the scale, or have a lower level on the decibel reading, so I can see where my baseline is, what the noise is happening in the piping. After that, I'll come in and I will test right at the discharge orifice of that steam trap and watch what's happening there. After I've done that one, so if, for example, this steam trap is blowing through, I should have 20% of scale at this point. At this point here, that needle is going to be pegged over to the far right-hand side of the scale, and it's going to be very loud as that condensate, or excuse me, that steam is blowing through that orifice and the restriction in the steam trap. What I can do then, just to verify that the noise is coming, and the point of most ultrasound is typically where the most turbulence is being created, I just want to confirm that that is coming from the point over here rather than something downstream. So I'll also listen downstream of that steam trap and make sure that there's not a higher ultrasound level further downstream. So if I'm testing this steam trap, I come and get my 20% reading here, come over here, get 100% of scale and a lot of noise blasting through, and I come over here and I'm back down to 30–40% of scale, then I can tell that this particular point here is where the most ultrasonic noise is being created. I can call that trap failed in the open position. If I come in again though and test, and I'm 20% here, I get a high level of sound here, I'm at 100%. What I'll do is I may turn that sound down a bit or turn the sensitivity down a bit, so it's maybe sitting at 50% of scale. I'll come down and test on the far left-hand side over here. At that point, instead of being at 50% of scale, it's back up to 80–90% of scale. Then I can understand that the ultrasonic noise or the most turbulence is being created even further downstream of that line. So at that point, what I'll do is I'll keep moving down the line until I find the source of the ultrasound, try and isolate it as best as possible, come back and test that trap to see if it is actually blowing through or not, or if the ultrasound downstream was giving us that false signal. So getting into the different types of traps, there's a number of different types of traps we want to look at. We'll look at an inverted bucket, flow and thermostatic, thermodynamic, and thermostatic. I mentioned there's two primary ways or two prime operating modes for the steam traps. Inverted bucket is an on-off trap. So when we're testing this trap, we are looking for a specific on-off cycle. The way that the trap works is, and we're showing the trap here in the condensate mode, so we're discharging condensate. Condensate's going to flow into the bottom of the bucket, and as an inverted bucket name sounds, there's an inverted bucket inside there. So the way that this trap works, get my mouse back here, is the weight of the bucket will actually overcome the closing force, and it's a differential pressure that's occurring through this orifice here that actually closes that trap. So there's the valve stem, valve seat. As the condensate comes in, fills up, the weight of the bucket will actually cause that bucket to drop down, open that valve, and allow the condensate to discharge. When it's discharging, we should see that needle pegged to the right side, and we'll hear a fairly loud noise coming through there. As live steam comes in, it's going to start to fill that bucket up. That bucket's going to become more buoyant. And as that bucket becomes more buoyant, it starts to lift up. And as we lift up, the differential pressure between the inlet and the outlet will actually suck that stem into the seat, and that valve will close. And generally, we see these traps cycle about, at most 2 to 3 times a minute. If it's cycling more than that, then we're a little bit inefficient with that particular trap, or maybe we're a little undersized on it. So I can run you through a couple of the sounds here. A good trap. Now this trap is actually cycling a little faster than 2 to 3 times a minute, but we've got to sped up a bit so you can hear that distinct on-off cycle. So this is what we're listening for with a good trap, a distinct on-off cycle. So you could hear the discharge, and then it would get quiet for a few seconds, and it would discharge again. We're usually looking for cycling on these traps at most 2 to 3 times a minute. When we get into some of the larger traps, or especially around the boiler house, we may not see these traps cycle for 3, 4, 5 minutes. So the cycle can be fairly long, but the main thing we're listening for is a distinct on-off cycle. We don't want to see that needle pegged all the way to the right like we would with a blowing trap, which I'll play for you now. So with the blowing trap, we don't have any cycling. It's just a continuous discharge of steam going through that orifice. The needle will be pegged to the far right-hand side of the scale. Decibel level is going to be high. We're just blowing steam right through that orifice. Lots of turbulence going on in there to create lots of ultrasound. One other failure mode that you can find with these traps as well is a condition called loss of prime. And it generally occurs if the trap's been out of service or the steam lines have been shut down for a while, the trap's been taken out for a bit. And what basically happens with this is we dry that inside of the bucket up. So there's no steam, no condensate inside there. And what will happen when we start it up is we can overload the trap so that the bucket will never actually catch up. So when we're testing that, what we'll hear is the steam blowing through there. The trap will never get time to catch up and cycle. So you'll hear the steam blowing through, but underneath that steam blowing through sound, you'll also hear the metal bucket sort of dinging around or clanging around inside. So I'll play that one for you here right now. So you can hear the steam blowing through, and underneath that is a little hard to hear, but if you listen real carefully, you can hear that metal bucket dinging around inside there. The way that you check for that to make sure that the trap hasn't failed is we'll shut a valve on the downstream side for a couple of minutes. So let the condensate build up inside that steam trap. Then when we discharge the bucket, the condensate can blow through, and the steam will start coming back in again, allow the buoyancy in there to lift that bucket back up, and hopefully that gets the trap working again. If the trap's still blowing through at that point, then at that point we can classify that as a failed trap and move on to the next one that we're testing. Okay. So a couple different pictures here of the bucket traps, and they can be configured. Generally, your inlet's going to be on the side or the bottom of the trap, and then your outlet's going to be on the side or the top of the trap. And they can come from a variety of different sizes and shapes, from some of the fairly large ones that you see in the piping system down to the smaller one-piece units, which we have in that top right corner over there. Okay. Next type of trap we're going to look at is the float and thermostatic. As the name implies, there's two pieces in it. There's a thermostatic element and a float element, and we need to test both of those when we're testing the steam trap. For classification, there's two modes of classification on this trap. It's either going to be on steam traps, they're either on-off operation or they're continuous flow. Float and thermostatic is the only continuous flow trap that we typically test. Okay. So the way that this trap works is condensate's or at startup, we're going to be in the low condensate mode position. As we start to bring the steam system online, condensate is going to flow in, and this ball here is a closed ball, and it's going to start to float. And as it floats up, the condensate level lifts up. It pulls this stem away from this seat and allows the condensate to discharge. As we bring more condensate in, it moves further and further away and allows for a continuous discharge of that condensate. For process applications, this is our preferred steam trap, simply because we're continuously removing condensate away from our heat transfer equipment. So it makes the heat transfer process a lot more efficient than an on-off trap, which can typically back condensate up, or may back condensate up onto some of our heat transfer equipment and decrease the efficiency of that heat exchanger. Okay. So when we're testing this trap, there's a couple of things we want to listen for. Again, we'll get our baseline reading, or we'll set our sensitivity. Then I'm going to come in and I'm going to listen to make sure that we're not blowing steam through this particular point here. So I'm going to listen right about where my arrow is pointed through to. We're going to listen for a continuous discharge, and what I mean by continuous discharge is we're going to see that needle or that decibel level modulate smoothly on the lower end of the scale. So if I set my baseline reading at about 10% on the inlet piping at that discharge orifice, I should see the sound level at 20 to 30%, and the needle should move slowly back and forth between that level, maybe up to 30 or 40%, maybe a little bit higher. But we want to see a slow movement to that needle, just kind of lazily moving back and forth inside there. One of the other things we're going to listen for as well when you're listening to steam traps is a steam trap that's blowing, or steam that's coming through an orifice is going to whistle. It's going to be a much higher frequency or pitch than condensate. Condensate's going to kind of burble. So if you think of a stream that's flowing, it's kind of got a lower burbling, gurgling sound coming through than steam whistling through a smaller restriction. So it tends to be a little bit of a lower level, not so much of a hiss or a scream coming through. So this is what we're typically listening for the continuous discharge. So you can kind of hear it modulating there, a little bit of a crackling sound as that steam comes through, compared to a trap that's blowing through, which is just going to whistle like this. So a little bit of a higher frequency, a higher pitch as that's coming through. So that's what we're looking for there. The next area that we're going to test, after we've tested this particular point for the condensate discharge to make sure that float assembly is working properly, the next thing we're going to do is we want to make sure that this thermostatic element is working properly. Remember earlier I mentioned that a trap has three functions: to remove condensate as quickly as it forms, prevent live steam loss, and remove air from the system. The way that this trap removes air from the system is it uses a thermostatic element, and that's installed typically in the upper part of the trap. So over here, this is the thermostatic element. So what I'll do is, after I've got my reading down at this level and that needle's moving 20, 30% to scale, nice and gently moving back and forth, I'm going to come in and I'm going to listen at the upper part in this area here to see if that thermostatic element has failed. And if it has failed, the ultrasonic signature is going to be considerably higher here than it is down here. So maybe I'm at 80, 90, 100% of scale. I'm going to hear the whistling sound of the steam coming through. So those are the two areas we have to check on a flow and thermostatic trap. Okay. So testing, again, tested it in two places. Mentioned earlier, we want to see that needle sort of moving back and forth nice and gently in this area. If it has failed in the open position, it's going to peg. If the thermostatic element at B here has failed in the open position, it will be higher than we're seeing at point A if point A is working properly. Okay. And a couple of pictures of the flow and thermostatic traps. Again, typically characterized by piping coming in and out on the same side. Your inlet piping is generally going to be on the top. Your outlet piping is generally going to be on the bottom. There are configurations like the one in the top right-hand corner there, which will allow you to bring piping in one side and out the other. Just depends on the type of trap you're dealing with. Okay, so that's the flow and thermostatic trap. The next type of trap we're going to look at is the thermostatic trap, and these traps operate on they're temperature sensing devices. So they can either be balance pressure, there can be a metallic element in there that's going to sense the temperature change, and it's going to allow an element to expand or contract to drive a valve stem into a seat. So in this particular example here, we've got the BELLOWS, which has a liquid fill in it, and it's designed to about 3-4 degrees below the saturation temperature of the steam, those bellows are going to expand and drive that valve stem into the seat. So at startup, it's allowing the condensate to discharge, or when there's a large amount of condensate backed up in the system, it's going to allow the condensate to pass through. As the steam pressure or temperature increases, the liquid inside there is going to eventually expand, overcome the force that's working on the bellows, and drive that valve stem into the seat, closing it off. So again, it's an on-off trap. Instead of continuous flow, this is an on-off trap, so that's what we should be listening for when it starts. So what we'll look for, we'll get our baseline reading, be down maybe 10-20% of scale. When that trap discharges, it'll bring that needle and peg it all the way over to the right. We'll hear the discharge for a few seconds, then it should stop. So this is what we're listening for. So again, a distinct on-off cycle. These traps can take a while to cycle depending on the design, and if it's the bimetal one, you're subcooling the condensate maybe as much as 60, 70, 80 degrees. Depends on how the trap is set up. So the cycle can be a little bit longer than the one we just heard. Generally, you're going to hear that trap cycle, once every 20, 30, 40 seconds, somewhere in that kind of range. Just depends on the load that it's handling. As we get into a trap that's failed in the open position, this is what we're going to hear for that. So that was just kind of a continuous discharging sound. There wasn't any modulation, no on-off cycling. It was just a straight blow-through, and that's what we're listening for there. Okay. And a couple pictures of some thermostatic traps, the bimetal design, which is in the top left-hand corner there, or the balance pressure bellows, which is shown in this particular picture right there. So they can have a number of different configurations, a number of different designs. Just depends on the exact operating principle and the way that the manufacturer is, the element the manufacturer has decided to go with. Last type of trap we'll talk about are the discs, and basically the way the disc works is on Bernoulli's principle is kind of the background on it. And if we've got any pilots listening, Bernoulli's principle is kind of the theory that keeps the plane in the air, which basically states a gas moving at a higher velocity has a lower pressure. So the plane, because it's got the curved wing, there's a lower pressure on the top of the wing, which actually sucks the plane into the top of the air. Same kind of thing happens with these disc traps. So if we look at the picture on the bottom here, as steam comes in here, it comes through this orifice here, and there's your discharge orifice, and as it comes across this area here, it's moving at a higher velocity than anything at the top, so we get a lower pressure here, so it actually sucks that disc down to close the cycle. In the meantime, we've got steam in this upper cavity. There's a fairly large surface area, the cap area here, that allows the energy, the steam energy inside here, to start radiating off to atmosphere. And as it radiates off to atmosphere, that steam is eventually going to condense down. When the steam condenses down, it reduces in volume by about 1,600 times. When it reduces in volume 1,600 times, the pressure in the main line will overcome the closing force of the disc, allow that disc to pop open, allow the condensate that's built up in here to pass through, and then again the cycle will repeat. As soon as that condensate is passed through, the steam starts to come in, the velocity increases, the pressure drops, sucks that disc down. So these traps will typically cycle fairly frequently. You're going to see them cycling 3, 4, 5 times a minute. If they're cycling more frequently than that, then they can become a fairly high energy consumer. So we call that condition machine gunning or motor boating. We may want to think about changing that trap at that point, just from an energy efficiency standpoint. So what are we listening for with these traps? So a good trap, we're looking for that distinct on-off cycle, and it's going to sound like this. So we had a distinct on-off cycle there. If we have a trap that is motor boating or machine gunning, it's going to sound like this. And then the last mode is going to be a trap that's failed open, so we're not going to see any modulation, no open closing. It's just going to give us a straight blast through discharge. So those are the failure modes that we're going to see in that, or what the signatures we're going to hear on that style of trap. Okay. Installation with these traps, they can be installed in almost any orientation. So in the picture in the top hand left, you can see the trap is installed vertically. On the left, pictures on the right-hand side, we got three of the disc traps. There's one here, and then this third one is actually a disc trap as well, but it's mounted on a universal mounting device. Okay. So those are the disc traps. Okay. For a quick reference, again, the disc traps is going to be a hold, discharge, hold for some hold cycle, so an on-off cycle is normal mode. If it is failed, we're either going to hear very rapid cycling or the blow-through coming through. For the inverted bucket, also an on-off trap, so hold, discharge, hold. If it's failed in the open, we're going to hear dribbling, jackhammering, or just a whistle as it blows straight through. Thermostatic could be the bimetal or the balance pressure bellows. If it's failed in the open position, a loud continuous sound. If we're under very, very low load, under low pressure, or at startup, we're going to hear a bit of a steady modulating sound until it gets caught up. So at startup, we may not get a completely true picture of what's happening in there. But as a general rule, these traps are going to be a hold, discharge, hold, or on-off operation. Flown thermostatic is going to be a continuous discharge, so I should see a steady modulating sound. If we hear a much higher ultrasonic signature or the whistling sound, that's telling us that that trap has failed in the open position. There's one more device that's listed there. It's called the ORIFICE. We typically don't refer to that as a steam trap. A steam trap's an automatic valve that will sense the difference between a liquid and a vapor, allowing the liquid or the condensate to pass through while holding the vapor or the steam on the system. An ORIFICE doesn't do that. It's basically just a small hole drilled into a pipe union or an ORIFICE device. They are used in steam systems, generally on the higher pressure, 400 psi and above. But as a general rule for just modulating steam loads, we don't recommend them. They're not the most energy efficient device that you can get out there, but for higher pressures they do work well. If you are testing them on a higher pressure system or using them on a higher pressure system, you should hear a continuous discharge through there. Again, you'll hear kind of the crackling sound or the lower pitch sound if it's condensate that's coming through. If it is blown through or worn, so we're getting too much flow through there, then we'll hear that higher pressure, or excuse me, the higher pitch as it comes through. Okay, so that's kind of just a quick reference available for him. When we get into the testing equipment, there's a number of different options. With the ultrasound units can be the digital models, the analog models. The nice thing that we found with the digital models is the data logging capability that they have. It certainly helps capture some of the sound files as well, so we can do a comparative test if you have somebody new coming out with you testing the traps. And you know, trap number 125 has this particular signature. When you come back, you can do a comparison to it to make sure that you are still getting that same sort of signature, that same kind of sound. If there's something different, then it gives you an opportunity to do a little bit more investigation to find out what's going on. When we're testing the traps as well, with the ultrasound, obviously we want to be using that stethoscope module. We're going to be on the 20-25 kilohertz range, and we're going to have the unit set to log to get our real-time reading of what's going on inside that trap. Some other considerations, we kind of come towards the end of this here. One of the big things that we really emphasize is document and record the results. If you just go out there and test your traps and you just kind of put a bit of red flagging tape or whatever you're putting on the trap to indicate it's failed and you don't document and record your results, you're missing a really good opportunity to find out what's going on in your steam system. I mentioned a bit earlier about looking at the system as a whole and not just blaming the steam trap. Steam traps are notorious in the steam world for taking the brunt of the blame. The reason being, it's a $200, $300 device typically. And it's much easier to blame that $200, $300 steam trap than it is to look at the whole steam system and say, well, actually we've got a bigger problem with our piping, but it's going to cost me 10 grand to fix that. I'm going to blame this $200, $300 steam trap. So if we're not documenting and recording our results, we're not going to find out where the trends are. We're not going to see that the trap number 125 is failing every other month. And we need to look at actually why that's happening. So that's one of the big things that we do emphasize is document and record your results. Don't componentize the system. Look at the whole installation. I kind of touched upon that here just a second ago. The steam trap is a device that is going to fail after a while. We demand 6 years performance from any steam component, including the steam trap. If you're not seeing that, you need to take a look at why you're not seeing that. It may be that you're not selecting the correct components in there. You're buying a steam trap based strictly on price. Steam traps are like anything else out there. You can get something that has a 1-day warranty. You can get something that has a 2, 3, 6-year warranty. It just depends on the manufacturer. something that's going to give you a 6-year warranty is probably going to be a better quality than something that gives you a 1-day warranty. And if it's a better quality, you're probably going to pay a bit more for it. So there's the balancing act that you need to consider as you're running through there. Any failure that we see out there, we want to do a root cause analysis. We want to know why that trap failed or why that component failed, and it'll allow us to, again, improve the steam system, improve the efficiency, and improve the safety of anything out there. 6 years performance is what we're looking for. From the testing frequency, we want to test process and high-pressure traps every month, and then every other trap out there every 3 to 6 months. Tracing traps, bring the system up, or the unit heaters if you're bringing them up once a year. Kind of test them at the beginning and the end of the season to make sure that they're working properly. Why are we testing this? It's easy to sit here and say, well, we should be testing traps every month or every 6 months. And from a maintenance standpoint, we recognize that, but when we go to management and say, hey, I need to have 2 guys available to me to go out and test this trap, it becomes a little more difficult to do. There needs to be some kind of economic justification or some justification so we can go out and perform this testing. Steam traps are going to cost a lot of money if they are failed. The industry standard says about 10% of your trap population is going to fail on an annual basis. If your trap program is not in place, it's not uncommon to see 50%. We've been into facilities where you go out and you test the first 100 traps, and you see close to 100% failure. You go ask them, when was the last time I did a trap test? Well, it was 10, 15 years ago. So at that point, the trap testing is almost an irrelevant procedure to go through. You're almost better off just replacing all the traps and starting fresh, because you are going to see failure in these things. They're doing an awful lot of work. They're seeing an awful lot of abuse. They are a maintenance item that are out there, so you do need to be willing to repair them and replace them and test them on a regular basis. If that trap has failed open, in addition to the energy costs that we're seeing, we're also going to see production and emissions effects on it as well. The trap that's blowing through, we're not leaving the steam on the heat transfer equipment long enough for it to give up its latent energy, so the efficiency of that system has dropped dramatically. And the emissions as well. Literally tons of CO2 and NOx are being discharged through these traps and fail in the open position. So we can certainly generate reports that show that kind of thing. DOE has some phenomenal resources for us when it comes to steam systems and testing steam traps. This particular one, the numbers are a little bit older, but we can certainly update them for our own facilities depending on what we're charging or what our steam costs are. So this particular example, they're using $4.50 per 1,000 pounds. That's a number probably dating back 7, 8, 9 years. I mentioned earlier our steam numbers now, or our cost of steam now for an unloaded cost, and that's just the fuel we're burning to produce the steam, is generally in the $10 to $15 per 1,000 pounds. So you can take these numbers and double and even triple them fairly quickly. If we look at a steam trap with a 1/8 inch orifice, so if we're looking at the 1/8 inch orifice on the left-hand side, and we're running in a steam system at 150 psi, it's telling us we're losing 75.8 pounds per hour. If we look at that, multiply it by 8,760 hours per year, and by $4.50 per 1,000 pounds, that trap's costing us about $3,000 a year in lost steam. If it's just dumping to atmosphere and dramatically reducing the efficiency of the system. If we increase those to today's numbers, where we're 2 to 3 times that, then we're obviously $6,000 to $10,000 worth of wasted energy going through there. And nobody can afford to have that in a production facility where you have a trap population of 1,000 traps. You figure 10% failed on an annual basis, multiply that $3,000 by 100, and right there, the trap maintenance program is a very, very cost-effective program, and the payback on it is typically within 2 to 3 months on this kind of system. Okay. A couple of quick energy facts closing out here. Over 45% of the fuel burned in the U.S. is burned to produce steam. Typical facility can realize steam savings of 20% by improving a steam system. And we're talking the low-hanging fruit here. So the low-hanging fruit is testing your steam traps and replacing them. That's probably the easiest thing you can do. The second thing is go around look for the steam leaks. By doing that, you can dramatically improve the efficiency of your system and realize some significant savings as we go through and work on our steam system. So last couple of things, a couple other quick impacts on the leaking traps. Emissions. If you're not focusing on the CO2 and the NOx and the other greenhouse gases at the moment, wait for it, it's coming. We're seeing it up north here where the government's starting to regulate us on a lot of these things. It is coming down south where people are focusing on the CO2 capture, the NOx capture, and if you're not maximizing the efficiency of your boiler and the throughput on your steam system, you are producing these gases and they are going straight to atmosphere. So by having a very proactive steam trap maintenance program, you can reduce these numbers dramatically. So I would highly recommend getting in and testing the traps on a regular basis. Okay, so that's it for me. Thank you very much, and I will pass it back to Gary. Thank you all very much. Appreciate it.
Thank you, Tristan. That was tremendous. Story you're telling us about steam and how to test those steam traps. We really enjoy that. Let me just get my computer coming back on here, and we're ready to go. That was great information we have from Tristan. We really appreciate you taking your time today and going through this with us. This will be available up on UE website for recording later. So again, without going back through that, thank you, Tristan. Other things that we have available for opportunities that we can do things with UE Systems here is we have 2 steam trap inspection courses going on, one in Clemson, South Carolina, coming up in November, one in December up in Fargo. We've added another one for, I think, for February and March. I don't have those on here. They'll be up on our website if people are interested in attending those. Those are 2-day courses where Tristan or people like Tristan take you around a plant and actually assist you in testing steam traps and gain some experience. We got 3 one-day classes on steam systems, optimization of steam systems happening in November, one in Milwaukee, one in Atlanta, one in Los Angeles. And so we're going to go around the country and see if we can get people doing a better job in their steam systems. And then in the same line of things, we've got in energy conservation, we've got a couple compressed air classes coming up this fall. In October, we got one in Dallas, then another one in California. I think in November, we got one coming up in Canada. So we have details on all the different training options up at uesystems.com. We also have other information on their steam trap testing. We've done previous webinars like this on bearing inspection, electrical inspection, and they're up there. We have lots of information up there that you can go get. All that's at no cost, and it really can help you do a better job on your plant. We're planning another webinar here at the end of next month. I think we're going to do it on compressed air and energy conservation, staying on that same sort of theme is what we have in mind. You can contact Tristan or any of the people at Swedgelock Energy Advisors at swedgelockenergy.com. I put it up there, Tristan's email, tristan.mccallan@swedgelock.com. Be happy to answer your questions. I hope he doesn't get flooded with a whole bunch of stuff and then he ends up mad at me, but Tristan's a good guy. I'm sure he'll help you out. You can always contact us here at 800-223-1325, or there's our local phone numbers on our website as well. So with that, I want to thank everybody again for taking all your time and joining us today, and look forward to future ones that we do. Thank you.